Hi there. I'd like to talk a little bit about quadratic modeling. First of all, let's suppose we were given this data that's in this chart. And if we wanted to know if this could be modeled by a quadratic function, there's a really clever way of doing that. First, we would look to see if there are common differences, and each of these is different by 1, so that works. And then we would look at the differences of the consecutive points. So, for example, the distance between 11 and 21 is 10. Between 21 and 35 is 14. Between 35 and 53 is 18. And between 53 and 75 is 22. So these are called the first differences, and then we look at the second differences between them. And what we'll notice is it's 4, 4, and 4. So if the second differences of the independent variable, in this case, the dependent variable, the y, are constant, then we know that it's modeled by a quadratic equation. And that's just kind of a clever way of looking. There are other ways of doing it. So let's say we have this and we want to create the quadratic function that fits this data. So one way to do it is consider that we've been given 3 points, 311, 421, and 535. So given these 3 points, we can think about the fact that we know the standard form is y equals ax squared plus bx plus c. And by using this, we can substitute what we know for x and for y into that standard equation. So for example, for the first point, we would have y, which is 11, equal to a times 3 squared plus b times 3 plus c. For the second point, we would have 21 equal to a times 4 squared plus b times 4 plus c. And for the last one, 35 equal to a times 5 squared plus b times 5 plus c. And I think you can see where we're heading with this is that this very neatly creates a 3 by 3 system. And I'm going to multiply these out, square these out, and then mix it up or flip it around a little bit. So I get 9a plus 3b plus c equal to 11. And I have 16a plus 4b plus c equal to 21. And I have 25a plus 5b plus c equal to 35. So here's my 3 by 3 system, and I can solve this to find a, b, and c, which will give me the coefficients of the quadratic equation that fits this data. So how am I going to do that? Well, I could, in order to solve this, I could use possibly elimination, and you can see how that might be easy because each of these have a 1c, so you could get rid of c's first. But I'm going to think about a quicker way since we know now how to do it with matrices. So if I create a matrix equation for this, it would be 9, 3, 1, 16, 4, 1, 25, 5, 1. That would be multiplied times our coefficient matrix, which is ABC, and that would be equal to our constant matrix, which would be 11, 21, and 35. So if I called this A and I called this B, then I would know that my answer, let me write it over here, A, B, C is going to be equal to A inverse times B. And if you do that in your calculator, you would get for an answer 2, -4, and 5, which means using that information from our, and put that into our standard form, we'd have y is equal to 2x squared minus 4x plus 5. And that would be the equation that models that data. Okay, so that's one way of doing it. There's another way that's calculator driven, and let me just erase this. The other way to do this is very much the way you did it with linear functions. We can use the stat function, and we can list L1 and L2 in our stat plot and get 3, 4, 5, 6, 7, and under L2, which would be our Y, 11, 21, 35, 53, and 75. So with that information, what I want to calc in this case is a quad regression, not the linear regression, but the quadratic regression. And if you stick that in your calculator and then calc a quad regression, you would get y equal to ax squared plus bx plus c, where a equals 2, b equals -4, and c equals 5. And you would also get r, or the regression coefficient, is 1. So I think that's it. We'll do some work in class on this, and that's it.